Hello everyone, welcome to Midas Expert Web Convention 2022. So today we'll be discussing on pushover analysis. So myself Suman Dhara, so I'm working as a senior structural engineer at Midas IT. Before that I was working in Jacobs as a bridge engineer. So overall I have 7 years of experience in structural bridge design and I provide Midas technical support to engineering firms all over the globe. So these are the contents of my presentation. First, we'll look at the pushover analysis, a brief introduction that I'll give you. Second, we'll see how we can do pushover analysis in Midas Civil, where we'll cover the modeling aspects of pushover analysis. We'll detailedly look at the pushover hinge properties, which are available in Midas Civil. And we'll see a demo of a sample bridge with a substructure. And then we'll discuss the results. And later on, I'll take the Q&A. So let's talk about the general seismic design philosophy of bridges. In buildings, we follow the concept of strong column, weak beam, but in bridges it's reverse, where we want to have ductility built in the columns uh, while the superstructure remains elastic. So we allow the plastic hinges to form in the columns, allowing for localized inelastic rotations. So these hinges act as energy damping zones, and there will be cracking of concrete which changes the cross-section properties at these locations. Basically, the formation of the hinges allows the plastic deformation, which in turn reduces the peak elastic seismic design forces needed to be resisted by the bridge. So these plastic rotations of the plastic hinge occurs within a defined length which is called as LP, which is the length of the plastic hinge. So this is the plastic rotations. So these produce the delta P at the superstructure level. So you have the elastic displacements and the delta P. So combined would be your total displacement at the superstructure level. So finally, what we check here is the global ductility and the local ductility. In the global ductility check, we check whether our design ultimate deformation is less than our target displacement. And in the local ductility check, we see whether our plastic rotation demands are less than the plastic rotation capacity. So plastic rotation capacity can be determined by pushover analysis, which is delta PU, and gamma RP value is a factor to reflect the local defects of the structure or any uncertainties of the model. So Eurocode suggests guidelines about this, and recommended value is 1.4. So this is the formula for determining the plastic rotation capacity. So you have the ultimate curvature and the yield curvature and the plastic hinge length. Then we can determine the plastic rotation capacity and compare it with the plastic rotation demand. So to determine the displacement demands, we can use these three methods. One is your equivalent static analysis method as suggested by Eurocode or Astro code for regular simpler bridges. And we can perform a response spectrum analysis, which is a type of elastic dynamic analysis to determine the displacement demands of the structure, or a complete non-linear time history analysis for a given earthquake can be performed to determine the displacement demand. Next, for determining the displacement capacity, we can use a non-linear static analysis procedure, which is called as pushover analysis, which we'll be looking into detailedly in this presentation. And the other one is a complete non-linear time history analysis with inelastic hinges. So let's look detailing into pushover analysis. Pushover analysis is a nonlinear static analysis procedure that is used to determine the capacity of the structure beyond its elastic limit. So we try to understand the post-elastic behavior of the structure. So this is generally carried out after the linear analysis, where we freeze the sections, reinforcements, and we complete the serviceability and the strength design. So it majorly allows us to evaluate the overall structural behavior, the performance characteristics, the sequential formation of the plastic hinges in the individual structure elements. So all this can be evaluated. So finally, when we arrive at the displacement capacity by pushover analysis, then we can compare it with the displacement demand that is determined from the response spectrum analysis. So let's try to understand the concept of pushover analysis using a simple SDOF system like this. When we apply a lateral force of F magnitude, we can see a elastic displacement of delta 1. And if we further increase this lateral force to a certain extent, we can see the increase in the lateral displacements, which is delta 2 and delta 3. And after certain displacement, then we can see the yielding, that means the formation of the plastic hinge. So if you plot the force versus deformation curve, then you have the yielding point. For a given lateral load, then we can see an enormous increase in the deformations till we reach the collapse. So pushover analysis uh, allows us to investigate this entire post-elastic behavior of an earthquake resisting element, and we can obtain this sequential formation of the plastic hinges, and finally we can perform both the global ductility checks, the local ductility checks from the results of the pushover analysis. From now on, we'll look at how we can perform the pushover analysis in Midas Civil software. So the procedure of pushover analysis in Midas Civil software is fairly simple. So this is the flow chart describing the procedure. First, we start with the complete static analysis model where we completed the member design. Then we go to the pushover tab, we input the control data for the pushover analysis, like specifying the maximum number of increment steps, the iteration process, the convergence tolerance. And then we define the pushover load case where we can add the initial load, which is the dead load of the structure, or any other conditions. Then we use any form of static load case or uniform acceleration or mode shape for generating the pushover load that can be applied to the structure. So basically the load pattern. Then we define the hinge data. So we can define the hinge data representing the metal nonlinearity, the inelastic hinge. There are many types of hinge that are provided in Midas Civil software. Then we assign this hinge data to the members. Then we perform the pushover analysis. And after that, we can check the analysis results graphically, and we can also generate the chord rotation and all those tables from our result tables of pushover analysis. So we can check the performance levels of the structure against various design spectrums. We can check the deformed shapes at each step and the sequential formation of the plastic hinges. So first in the software, we have to define the pushover global control. So this is the dialog box from Midas Civil software. So here we have an option of providing the initial load. So we generally apply the initial load before the application of the lateral load pushover load pattern. So we have two options. One is performing nonlinear static analysis for initial load. So initial load can be self-weight or SIDL. or we can import the results from construction state analysis or any other static analysis. Next, we can define the stiffness reduction ratio of a skeletal curve of a hinge. So if a hinge type is bilinear curve, then we can provide the stiffness ratio, the reduction ratio for the first yielding point. And if it is trilinear curve, then we can specify the stiffness reduction ratios for the first and second yielding points. So those options are there for the user to edit. So step 2 is to define this push or load case. So here we can specify the increment method as load control or displacement control. So when we select the displacement control, we have an option of giving a master node, that is any node of the structure, and then specify a target displacement. So the load pattern would be altered in steps such a way that you would reach this target displacement in the pushover analysis. And the load pattern you can select from these 4 types. One is your static load case, where you can apply a simple static load of 1 kilonewton suppose, and the program will try to alter the static load to reach this target displacement. Then we can generate the load pattern such based on the uniform acceleration, which are nothing but the initial forces developed in the structure, or based on the governing mode shape, the load pattern can be generated, or a normalized mode shape into mass. So in that fashion also a load pattern can be generated for the pushover analysis. So step 3 is to define the pushover hinge properties. So we have 5 main components of pushover hinge properties. One is element type, metal type, definition and interaction type, and the component properties. So if we are assigning the pushover hinge to beam or column or truss element, we can select these options. Or to behave the pushover hinge in terms of point spring or general link, we can select this. We have metal type as RC steel. Then the load deformation behavior of the pushover hinge in terms of moment rotation or moment curvature lumped or moment curvature distributed, we can specify. Then we can specify the interaction type that will be used for the hinge. One is none, where we do not have any coupling between the axial force and axial moments. For PM, we have a coupled axial force between and the uniaxial moment behavior that the program will consider. And we also have this coupled axial force biaxial moment behavior that is used to calculate the fractional yield strength of a hinge considering the effect of change in axial force. Then we have the component properties uh, in the local directions fx, fy, fz, mx, my, mz for a particular element. So if we select the moment rotation, we have 3 types of skeletal curve of hinge: bilinear, trilinear, or FEMA we can select. For moment curvature M5 lumped, we can select bilinear type, trilinear type, and GSD import. So we'll see how we can use Midas GSD to import the hinge properties, where we can consider the inelastic material like the confined and the unconfined concrete properties for a pier section suppose. When we select moment curvature, we have 2 types, which is bilinear type and the trilinear type. So now I'll show you the quick demo how we can perform a pusher analysis for a simple bridge, where we'll take the bent cap. Then after the pusher analysis, we'll see the results, and finally we can see how we can do the global and the local ductility checks. So here I have opened a sample model. So this is a 2-span PSC composite bridge model, where we have the central substructure in this fashion, where we have a bent cap and 2 pier columns. Firstly, I have invoked the eigenvalue analysis control with 150 frequencies. So we'll later on check the mass participation factor, whether they are that has reached 99% or not. Then we have the material properties and the sectional properties. I consider 1.8 meter dia pier column. These are the girder properties and the boundary conditions. And then we have the elastic link and the rigid link and the load to masses. So we can go to the query and click on the mass summary table to see the masses in X, Y, and Z global directions. Some self-weight loading. Then I have invoked the response spectrum analysis functions. The design spectrum I have defined. You can directly define from the code, select Eurocode 8, select the parameters, click OK. And then we can define the response spectrum load cases, RSX. So in the X direction, so I have given the excitation angle as 0. That means the excitation is in X direction. And RSY is 90 degrees excitation angle. That means in the Y direction. Then we'll run the analysis. Before that, we have to use the stiffness scale factors. So this is to uh, have cracked moment of inertia for the PO columns. So to calculate the section stiffness scale factors, so we need to know the crack moment of inertia of the column. As we know the gross moment of inertia from the section properties, we can use that directly here. Go to the properties section, show calculation results. Here we have IYY, which is your moment of inertia. Then we can use Excel. I've copied this from the Civil, and we'll obtain this value from Midas GST. You can go to the tools, click on general section designer. Then we can link this to our superstructure model and select any PS section. This element number is 133. Click on import. So this is your section. Then we can define the confined and the unconfined properties. So this is our section. So we have the material property, everything has been imported from the software. So here the rebar data has been imported. So in the software, I have defined the rebar data from the design tab, column section data for checking here. Selected 38 numbers, P32 diameter and P20 as the spiral size. So here we can change the material property of the concrete to model material, and here I'll modify, select use nonlinear, and we can define the nonlinear property. We will select the Mander model here. Let's choose these default values, click OK. So now you can see the confined and the unconfined properties. Go to the confined area. So let's take the cover as 0.07. Let's define the Mander concrete properties. I'll select the circular hoop confinement steel section data. So this is the distance, the ds. So if we calculate, we get it as 1.61. Rebar data, take 38 numbers. The longitudinal rebar P32, this as P20, click. So 0.1, which we have given in the primary Mida civil model. As we have imported the section, the data has been imported. Click OK. Ultimate strain we can define based on Eurocode. The stress strain curve for the rebar, I'll take it as spark strain hardening. So these are the default ones. If you want, you can change them as per your need. Right now, let it be default. I'll click on the stress strain curve. So based on the input that we have given, so we have the confined and the unconfined stress strain curve of the concrete. So these are the values which the program has been calculated based on the Mander model. Click OK. Now we'll define the confined area 0.07. Select the section. Assign the section now. We'll save it with some name. So here we have to define one load combination. So though we are interested in knowing the crack moment of inertia and also the moment curvature relationship, this load information is not needed. But we can check the stresses for this load combinations in Midas GST program. Go to the options, design code. Here we have the Euro code. Go to the design and design section. Go to the moment curvature, display itemized, apply. So here we can see the crack moment of inertia. So I'll copy this to the Excel. So it's the value. So J effective can be calculated from the Eurocode clause with this formula. So I obtain the J effective and then for the scale factor as 0.312. So now we can go here and apply this scale factor 0.312. All the elements which have been assigned with this column section. So you can see the stiffness scale factor. So we'll be using this stiffness scale factor to incorporate the crack moment of inertia as per the Eurocode to this model, and then we'll calculate the displacement demand from the response spectrum analysis results. After the analysis, we can go to the results, vibration mode shapes, and we can check the frequencies and the time periods. So we can see the mass participation reaching 98% in the Y direction, and the governing mode is mode 7. So the frequency and the time period for mode 7 is 0.1805 seconds. So it's 0.1805 seconds, and T naught as per Eurocode you can calculate 0.5 into 1.25. So based on T naught and T we can calculate the mu D, which is displacement ductility factor as per Eurocode 8 clauses. Then we can take Q as 1.5, which is your behavior factor conservatively. Then we can calculate the neta. So neta is based on the formula given in Eurocode. Then by this formula, multiplying the neta into mu d into the displacement which is obtained from response spectrum, we would get the seismic displacement demand. So this displacement from response spectrum analysis we have to take from the software. We can go and go to the result tables, click on the displacement. So to note here, we are interested in the substructure, which is your bent cap, and we'll see the displacement demand which is obtained at this node. So in the pushover analysis, which we'll be doing next, we'll be taking this node as the master node. So at this node, what would be the displacement demand? So we'll go to the displacements. Node number is 168 for RS, X and Y. Let's see the displacements. So this is 0.00873. Copy this. So finally, we have calculated the seismic displacement demand, which is 0.033 meters. Now next we have to calculate the seismic displacement capacity from the Pushover analysis. So for that, to simplify the model, what we can do is we can delete the superstructure part and just carry forward this reactions from the superstructure onto this pier. So I'll open one model where we do not have the superstructure, but we have the reactions of the superstructure applied onto this vent cap. So to save time, I have opened this model, I have prepared this model. Just that I have deleted the superstructure and then applied this reactions from the superstructure onto this bent cap, and the sulfate is present. To calculate the sulfate of this substructure, we have the response spectrum. Now we'll start the Pushover analysis procedure. We can go to the Pushover tab, click on the global control. So here we have the option of initial load. So I'll select the sulfate, add, SID add. So this would be sulfate and SID would be considered as initial load. The program will perform a nonlinear static analysis for this initial load first, and then the pusher lateral loads would be applied. The rest all I'll keep it same, click OK. Next we'll define the load case, we'll add. Here I'll give a load case name as pusher X. Let's give it 50 steps, include the P delta effect in pusher analysis. Displacement control. So the master node that I'll consider is this 168. X direction. The target displacement in the X direction for this node, give it as 0.5 meter for now. I'll select uniform acceleration in the X direction, click add. So the load pattern would be generated based on the initial forces. Okay, click add, push Y, displacement control master node 168. Now I'll select dy here, 0.5 meter as the target displacement in the Y direction for this node. Select uniform acceleration, select dy, click add. So these two pusher cases I have defined. Next, let's define the hinge properties. So here in the hinge properties, I'll click on define pusher hinge properties, click add. So as we discussed earlier, that we need to select the element type as beam, and then we can select the moment curvature M5 lumped, consider the hinge length integration point at end of the element, PMM status. Then here we can have the skeletal curve as bilinear or trilinear or a GSD input. So if we are selecting the trilinear type, go to the yield surface properties, y-axis. So the y-axis, about y, we have this directional properties of the pusher hinge. So we can define this alpha 1 and alpha 2 manually here. So this is one type of pusher hinge, like the trilinear type. To capture the accurate PMM interaction for the pusher hinge for this column, we can use Midas GSD. So if we click on GSD import, we do not have any yield properties right now. So we do not have any yield properties here. So for using this GSD import type, we need to first link the model with the Midas GSD. So this is a model. So we'll link it with our substructure model. Go to the GSD, go to the moment curvature. Here we have the export option. Give the name as GSD Hinge 1. So we want the coupled axial versus the biaxial moment interaction. And here we have the hinge length ratios that we need to calculate. Calculated that in the Excel. So we know the bar diameter. Uh, the yield stress of the reinforcement 600 MPa that I'll take. So this L. So in the Eurocode we have this L, which is the distance from the plastic hinge section to the section of zero moment. That we can get it from the analysis model, which is 5.12 meter that I've measured. Then we have the hinge length. By using this formula, we can calculate the hinge length. Then we can divide LP by this L length. Then we'll get the ratio as 0.156. Go to the GSD when we click on export. 0.56, 156. Click. Here we can see the program is creating the data for the GSD hinge. So Midas GSD data has been completed. You can go to the model. So here we have the hinge that is generated. So direct import takes place from GSD to Midas Civil, which is linked. Go to the properties. So here we have the GSD import type, yield surface properties. So we have the PM interaction, the biaxial interaction curves in MY and the MZ directions. In the component properties, so this moment curvature would change based on the axial force. So the user defined axial forces are generated. You can also give them in the GSD where at specific axial forces the moment curvatures would be imported. So you have the yield strength, yield curvature, you have different axial forces based on which you have different moment curvatures. Similarly for the Z direction, you have the hinge length ratios. So this completes the pusher hinge properties. Now we'll assign this pusher hinges to our elements, beam elements. So here we'll for this type of bent column structure, we know that the bending moments are larger at this locations. So the hinges would first form here. So I'll be selecting these elements for assigning the plastic hinge with this property. Click apply. These are graphically displayed. Now we can perform the analysis, then perform the pusher analysis. So this is the pusher curve in X and Y direction. So we can see here this is the hinge deformation. So I think we have 0.5 meter, which is larger for this type of structure. So we can reduce that. Nevertheless, we have here the capacity curve, the base shear versus the displacement that is plotted. Then we have the performance point that can be generated based on the design spectra. So we have the performance coordinates here. So this is your performance point that we can obtain. We can go to the reactions. We can see the reactions for various steps. Turn on the legend and see how we can the reactions change as per the push. You can check the deformations in various pushover steps. We can set the element yield status. So at second step we do not have yielding. Then we have at the 5th, 17th. The first yield occurs at step 9. So like this we can determine at which step the hinge would occur. Based, you can set the you can check the deformations. That step you can check the forces similarly. So these are the bending moments. Check the shear forces. On the columns, you can similarly check the stresses. We can plot the pusher curve, pusher graphs, pusher hinge properties, pusher hinge table, and then the pusher hinge results. The yield step, you can select pusher and click OK. So this tells you at which point you have the yield. So it is at the step 8 where we can see the yielding at this element location. You can see the forces in tabular format. We can get the deformations in the tabular format. So that's how you perform pushover analysis in Meda Civil software. This is a brief introduction to pushover analysis, a realistic view of how you can do it with Eurocode 8. Now finally what we have to do is we have to check the global ductility checks and the local ductility checks. So we have to get this displacement capacity from pushover analysis. We can go to the pushover curve, and right now I'm considering pushover Y. So here we have the yielding that is occurring at 0.08 meters. This is my capacity, and this is the demand that we have extracted from response spectrum analysis. So as capacity is more than the demand, so the global checks is okay as per Eurocode. Then we can do the local ductility check. So for that we have to calculate the rotations, the ultimate rotations, the plastic hinge rotation from this formula. So the program does that. We can go to the pushover hinge results, click on chord rotation check, pushover Y, select the absolute max, and in the RZ, and go check the element local direction. So this is about Z direction, so that is RZ rotation. So here we have the plastic rotation demand, length, hinge length, yield curvature, ductility, yield rotation, and the ultimate curvature. Finally, we have the plastic rotation capacity. So we can copy this to the Excel because we also have another parameter called the gamma RP as per Eurocode, which we can take it as 1.4 conservatively. We can divide it with gamma RP, this formula. Then we can compare this factored plastic rotation capacity with the plastic rotation demand to make sure that plastic rotation capacity is always greater than the plastic rotation demand. So this completes the local ductility check. Local ductility checks and the local ductility checks demonstrate it. Okay, so to summarize what we have discussed in this webinar, first we have seen the seismic design philosophy, the theory behind the pushover analysis. Then we have seen how we can do the response spectrum analysis and then determine the displacement demand, and then create a model for pushover analysis. So we have detailedly seen the steps of pushover analysis, and then we have obtained the displacement capacity from the pushover analysis. Then we have seen how we can perform the global ductility check and the local ductility check, obtain the plastic rotation capacity from the Midas Civil software, then compare it with the plastic rotation demand. So that's all for today. I hope you have enjoyed the presentation. So thank you so much for attending this webinar. Now we can go for Q&A.